So we will actually look into this giant ionic lattice. So the important thing about this giant ionic lattice, this is going to be for ionic compounds. Okay, ionic compounds, we know that they have metal and non-metal joined together. So if you have Na plus and Cl minus, I know that the forces of attraction that holds them together, because there is a transfer of electron, the forces of attraction is called electrostatic forces of attraction. Electrostatic. Okay, so electrostatic forces of attraction. Okay, so these electrostatic forces of attraction, we don't I think if you call them ionic bond, yeah, that is electrostatic forces. Okay, so because of positive and negative, we call it electrostatic forces of attraction. So this one we have learned that, okay, lattice is a regular repetition of arrangement. So this one will create a 3D arrangement according to your syllabus. There are two ionic compounds, okay, that they mention in the syllabus, which is sodium chloride and magnesium oxide, but they are not limited to only these two compounds. Okay, it can be maybe LiCl, it can be Na2O. Those are also will form ionic lattice. Okay, but when it comes to arrangement, or when we show the diagram, they want us to focus on this NaCl and MgO. So the arrangement is going to be in cubic form. So you have this cube, okay, and this cube are going to have alternate chloride and sodium. So if let's say I take this one particular cube out, the smaller cube, okay, so if I make it bigger, okay, you can see the green part is going to be the Cl minus, and Na plus is going to be the yellow. But when we actually ask, okay, in this lattice, okay, each sodium ion is surrounded by how many Cl minus ion. So this one, maybe I'll ask someone, Frederick, how many Cl minus ion will be surrounding Na plus?
4.
Okay, when you see here, or when you just simply look at it, it looks like 4, okay, but I will show you. Okay, here, okay, this is Na. If you look from this diagram alone, you think that it's going to be 3. Okay, but do remember, we take from this bigger diagram. So if let's say I go into something that is in the middle, yeah, this is going to be an Na plus. You can see that they have 1. Okay, this one, this one, this one, this one, and this one. So 1, 2, 3, 4, 5, 6. I want you to memorize this. Of course, you no need to know how to draw. Sometimes if you look in YouTube, they actually show some students how to draw. Okay, but it's actually not important for our syllabus to learn how to draw. So this one you just memorize. Each sodium ions is surrounded by 6 chloride ions. Okay, now if we change this question, how about each chloride ion is surrounded by how many sodium ions? So maybe we'll ask Owen, how many, Owen? How many you think? Chloride ions? So if you have chloride ions, it means the green, yeah? Okay, each chloride ion is surrounded by how many sodium ions? Owen, are you there? Owen is not there. Is that Owen? Owen, where you go? If you are going somewhere, please let me know. Yeah?
Sorry, just I'll go toilet, sir.
Okay, please let me know next time. Okay. Anyway, Ewan, can you tell me each chloride ions are going to be surrounded by how many sodium ions?
According to the diagram, sir?
Yeah, according to the diagram. Which
Maximum
diagram? Depends which diagram you're looking to.
5.
5. Okay. But if you look over here, okay, I think you need to do remember this only a certain portion of it. Okay. Just remember it's repeating. Okay. So if I choose 1, okay, I think let me choose a very the suitable one. Yeah. Maybe I think I'll choose this one. Okay. So if I choose this one, imagine there's one more is going in front here. Okay, one more is going in front. Okay, so here, okay, or you can actually just take it as this one that is going behind is coming in front. Imagine there's another one more. Okay, I hope you can imagine. Yeah, so I'll just erase this part. Actually, if you look at each, okay, each is going to be bonded to 1, 2, 3, 4, 5. Okay, but there is another one that will also come over here. Okay, or I think if you look over here, this one will be a more accurate representation. Okay, 1, 1, 2, 3, 4, 5, 6. You can see that. Can see even? So you need to select the one that is suitable to see, but each of them, okay, each of these ion here, each of these ion are going to be surrounded by 6. Okay, it means because of cubic structure, so they are going to face 6 other atoms, okay, over there. In this case, ions, okay, 6 other ions. So they are going to be arranged. Do remember, this is not, this is just a simple representation. So these cubes, there are many cubes, okay, there are many cubes. And let's actually look at these properties of these giant ionic lattices. Okay, they are hard. Okay, why they are hard? Because there's going to be a lot of electrostatic forces of attraction between them. So it's difficult to be broken. Okay, difficult to be broken. Okay, but when it comes to this, when we say difficult to be broken, also, yeah. Okay, it depends on how we define difficult to be broken. Yeah. Because giant ionic lattice, okay, they are brittle. Brittle means, okay, can be broken also. Okay, so it means hard. It's quite relative, yeah, when you actually define hardness. Okay, when you actually try to scratch ionic lattices, you don't see scratch because they are hard. Okay, but when you actually put them, okay, with a high amount of force, okay, or impact, what will happen? Okay, the giant ionic lattices will break, brittle. Okay, this one I think last time, okay, I always like to actually refer using this diagram. Let's say a diagram of a person. Okay, and then, okay, I'll just quickly draw something over here. Okay, so imagine you go and punch this guy. Okay, and then the guy, the shape of the face will also change according to your the way that you punch. Okay, and then imagine you actually take something, okay, and you hit him, and then the head will break. Okay, or imagine you pull this guy's ears, the ears will become elongated. Okay, so how do we actually represent the details over there? Okay, the details, I think this one you can remember when it's something or metals becoming long or elongated. Okay, we call it ductile. If let's say the metals, you actually put certain kind of force, the metal actually change shape. Okay, can be hammered into different shapes. Okay, so this one is called as malleable. Okay, this one is actually if something can break easily, so we call it brittle. Okay, so here, okay, of course this one is not representing metal. Okay, it's just concepts. Okay, so here, okay, when it comes to brittle means they can be broken easily. I'll explain to you why they can be broken easily. Imagine if you have positive, negative, positive, negative. Okay, and then you have negative, positive, negative, positive. Imagine this is going to be a giant ionic lattice. Imagine there's something, a force of impact comes, okay, and then what happens? Okay, the layers, okay, will be disrupted, okay, and they will move here, they will move here. So let's say if I put them as moving, okay, maybe I erase this. So when they move, this one will become plus, okay, this one will become negative. So I just put negative here, plus over here. So what happens over here when there is a force of impact or any kind of force of impact? Okay, new arrangement will be formed. Okay, so you actually put something with a force. So what happened? Okay, they will slide first. Okay, they will slide. A new arrangement will try to they will try to form a new arrangement. but the arrangement will not last, okay, because, okay, positive and positive, okay, and then when you have negative negative, positive positive, so this one, okay, if I have this, okay, maybe positive, okay, this one is negative, yeah, so this one is negative, okay, when you have this, okay, you can see same charges, okay, same charges, what they will do, they will repel, okay, they will repel. So what happens, the new arrangement, okay, they won't be able to form the uh, electrostatic forces of attraction. So what will happen, they will repel, they will push each other. Okay, when they push each other, this is the time when you have that forces of impact. Okay, this thing will crack open, okay, and then there will be a chain reaction until they will crack, okay, and then they will break. So this is what we call as brittle. Okay, this is brittle because new bonds cannot be formed anymore because the same charges are going to be arranged side by side. Okay, so that's the problem with giant ionic lattice. Now, of course, they will have high melting point and boiling point because of a very strong uh, electrostatic forces of attraction throughout the lattice. Okay, and then we also have, okay, we also have, okay, a situation where this giant ionic lattice, okay, they are going to be soluble in water. Okay, so this one we have actually learned earlier, okay, where we have Na plus and then Cl minus. Okay, we know that each of them, they are bonded with ionic forces of attraction, which is electrostatic forces of attraction. So when you dissolve them in water, so what will happen is going to be, we know that this is delta positive, delta negative. So if let's say we have O delta negative, H and H delta positive. So what happens over here is there will be some kind of forces of attraction that will be formed between this positive and negative. Okay. So these forces of attraction will be quite strong, okay, where they can actually overcome these electrostatic forces of attraction. Okay, and then these forces will be broken. So you will have Na plus and Cl minus as free moving ions. Okay, so these forces of attraction, what is the name of these forces of attraction? Benedict, can you tell me? Last time I have actually mentioned this in class. Not sure, just say not sure, then we can move on to another person.
Not sure, sir.
Okay, Megan?
Is it the ion?
Yes.
Nick,
Okay, this one
dipole.
is ion and this is dipole. Okay, so they are called ion dipole bonding. So ion dipole bonding will be there. So this ion dipole bonding is going to be stronger and they will pull the, or they will break the electrostatic forces of this NaCl, even though despite the fact that they are going to be arranged in this manner. Okay, what happened? Each of them, okay, will be pulled by this ion dipole forces of attraction, each of them. So the entire structure will be broken. So you have, even though they are like this, the boiling point and melting point is really, really high. But because of the presence of water around them, they will form the bond. And this ion dipole bonding will break all these electrostatic forces of attraction. And then they will move away from each other. So that is going to be, okay, the reason why, okay, ionic compounds, they are soluble in water. Okay, we also have, okay, a situation where, okay, these giant ionic lattices, they can conduct electricity in both molten and solution. For solution, I think you should know already, the moment they form the ion dipole bonding, okay, they will have free moving ions. Okay, free moving ions, they can conduct electricity. Okay, but when it comes to molten, the same. Okay, when you have molten condition, they are not going to be arranged in this lattice anymore. Okay, so we also have sodium ion and then Cl minus ion as well. But sometimes people actually tend to confuse themselves. Like for example, if you have NaCl solid, okay, when I melt NaCl solid, what do I get? I get Na plus and Cl minus, but the difference over here is this one is in liquid. Okay, that's a difference here. This one is in liquid, but ions. Maybe last time you learned that your teacher say, oh, every single time there's ion, just put aqueous, not all the time. Okay, so please, whenever molten, so you will have ions in liquid form. But if you have in aqueous form, okay, let's say you add water, sodium chloride, let's say it's going to be, if I put the solid over there and you add aqueous, okay, water, you are going to get Na plus, then only they are going to be aqueous. Okay, that's the difference. But whatever it is, both of them are free moving. Okay, both of them are free moving. So when they are free moving, okay, when you have free moving ions, okay, they can actually conduct electricity. Okay, that is important. So they are not able to conduct electricity under the lattice form, which is going to be NaCl. When they are in solid form, they do not conduct electricity. Okay, so take note of that. The same applies, I think, even for HCl. HCl, they are covalent molecule. Okay, so covalent molecule, okay, they are in liquid form or gas form. Okay, they do not, okay, conduct electricity because they are covalently bonded. Okay, but okay, when you actually add with aqueous, okay, when you add water, okay, what happens? You are starting to get H plus and Cl minus. Okay, therefore they can conduct electricity. Okay, so this one is similar to this HCl as well. Okay, so they are again, explanation is the same. Why they do not conduct electricity? Because they exist as molecule. Why they can conduct electricity? Because they are free moving ions. And why this one cannot conduct electricity? Because not molecule, they exist as a giant ionic lattice. Okay, so they do not have free moving ion. But why they can conduct electricity in molten and solution? Because they have free moving ions. Okay, as simple as that. Okay, so this one, okay, is going to be properties of giant ionic lattice.